Okay, so today we'll be talking about threads, and so this is like the new module where we'll be talking about concurrency in general and how concurrency is made possible is using threads. So till now we had been looking at okay, it's not 20, it's 15. Just a minute. Okay, so till now what we had been looking at were single-threaded programs. And they have like one point of execution. At any point, like there is one line or an instruction in the program which is getting executed. But in multi-threaded programs, they can have multiple points. At the same time. Or in other words, what they can have is like multiple program counters. Okay. And these program counters belong to separate threads. And basically, each thread is like a separate process, except it shares like they are in the same address space, so they share the same memory. And this can share data also. Okay, so we'll come to how to implement these things and so on. But the basic idea is that basically to make things parallel and you want to run many things at one time and so on. So for that, this idea is used. And so what about, so when we started with processes, when we started programs, we were first thing that we saw is like state of a process, right? So similarly, what are the states of a thread? So this is very similar to state of a process, except like just like a couple of differences. In fact, like when we talk about state, so what did state consist of? Whatever its address space was, whatever the registers were, and these things. So each thread has its own program counter, other registers. So actually, it's like, yeah, we can say that it's exactly the same in some sense. Okay, so and then a thread will go into block state while waiting for IO, and then it can be ready. It can be, so yeah, again like ready, blocked, running. Okay, there's no etc. here in this thing, but these are the like this will use just like we did for processes, we'll be using this for threads also, that whether a thread is blocked, a thread is ready, a thread is running, and so on. So now similarly, like processes, we have to talk about context switches for a thread. And again, this is also very much like process context switch. Just that now there is a new, like, so for processes, all the data was stored in this thing called PCB or process control block. But in case of threads, it will be stored in something which is like, which will have per thread things, and it is called thread control block. And it is abbreviated as TCB. And also that, when you just switch between one thread to the other of the process, the address space remains same. So now you don't need to, like, go and look for, like, the new page in the memory, and, for the new thread and so on. The address space remains the same. So just to, like, how does the address space look like? So suppose this one is single threaded. So this picture we have seen like many times. Code, heap, stack, and in between memory is free. And here how it's going to look like. So this is multi-threaded. And again you have code, heap. Now instead of one stack, you have many stacks. Suppose then this is stack 2. So on. So these different stacks are for different threads. Free. Okay. So this only has a single stack at the bottom. Of address space. And here each thread since runs independently. So, and they might call also different routines. So they need to have their own stack. So we need one per thread. So here, like suppose there are two threads, then there are these two stacks, stack 1 and stack 2. Okay. And this is fine, like this works fine if the stacks are not too big. So we'll not worry about right now for the stacks being big and so on. This strategy is like, yeah, it's not the optimal. It does not keep the like, the nice picture that we have here, that okay, stack goes in this direction, heap grows in this direction. Here, like, there are separate stacks. Of course, the heap goes in the same direction and so on. But yeah, we have to do with it because now we want to run like multiple things at the same time in the process, which have their own stack and which also use the address space. So it does not look so pretty anymore, but you have to make do with what you've got. Okay. So yeah, so the stack for the thread is also called thread local storage. This is a stack. Yeah. Is there a question or something? Variables, function parameters, return values, etc. So all these will be so whatever will be on the stack, which is for a particular thread. So those things are going to be local for that particular thread. Okay. So now the question can come that, okay, why use threads at all? What advantage does it give? So there are two like main, let's say, advantages or uses. One is like parallelism. Of course. So what do I mean by that? That suppose, okay, so I have some task like to increase all elements of an array by a fixed constant, let's say. Okay. So I have an array, I have the entries, and suppose I want to do plus 10 to all entries. Okay. Now, so this is a 0 to whatever, a 20,000. Now, if we have a like only a single processor, then the only way to do this is perform each addition like one by one. And then it is like there's no other way. You have to go to every entry and increase that. So you don't really need threads for this. But like if you have multiple processors, then we can maybe try to divide the work. Okay. So that it can be performed on multiple processors together. Processors together. And that is where threads come in. So this is called, of course, parallelization. And threads allow one to do that. Okay. There's another like reason why threads can be useful, and it is to avoid blocking of programs which are waiting for IO. So what can happen is that a program is like making multiple input-output requests and so on, and it's like basically waiting the whole time, and no like useful thing is getting done at that point. So suppose X and waits in blocked state while IO is being performed. Now, maybe we don't want this to happen. And maybe we want the program to do some job. Uh, Something useful, maybe perform some computation or whatever while it is waiting for IO. And that's where threads allow this. So then we use threads. So what will that give? One thread can be waiting in blocked state, waiting for IO. And then the CPU or the OS switches to another thread, which will do the useful task. And then, like, when the IO is done, and then the first thread can come back and so on. So this is very similar to what happens. So thread allows overlap of IO with other things within the process, right? Just like multi-programming did across processes. So in multi-programming, if one process is waiting for IO, then other processes can be scheduled and some useful work will be done. But that is across processes; they are like different processes. And uh, if we want that to happen within a process, then we do this. Now the question can be that, I mean, then why bother with threads at all? Like, why not just go for different processes? Because these mechanisms are already there that, okay, one process is blocked and then the other can do. If one process goes for IO and, so on. So, and if there are multiple like processors, then the processes can run independently anyway. But so, I mean, tasks can be accomplished by different process also, but threads have an advantage. So what is the advantage?
Share the memory.
Yes, they share the memory. But threads share address space. So easier to share data. Okay, so threads are better choice if we want to do computation on some shared data, and processes can be a better choice if no data sharing is happening. So this is the main, advantage or reason for using threads, and yeah, uh, and it is better than processes in certain sense. Okay, so let's just get into an example. So okay, so now we want to write a program, and simply we just want it to print like different things. So want to create a program that has two threads. One prints letter A, and the other prints letter B. Okay. So this is one program, and okay, so let me stop the screen sharing here, and let's look at that program on the computer. So presenting. Just a moment. Okay, so share screen. Okay, so can you see my screen?
Yes, sir.
Yes. Okay, good. So this is a program that basically does what I talked about. So let's not worry about the headers for now. So they are standard headers, but at least the programs given in the book, they also use this, a little bit of, they just want it to be error free. So they assert using just one more variable, and they just change the names slightly. So it's not a big deal, but let's see what the program is doing. Okay. So this is the function that basically prints the character. So it takes threads take word pointers and they return word pointers, so that the structure has a word pointer, so that whatever you want to return, you can cast it and just send it as an argument, and also you can return anything. Okay. So here we don't want it to return anything basically. So we just want it to have this. So this argument is going to be basically the string, and then we just print this argument or this string. So we print this character pointer, which actually is the argument for this function, and then we just return. Okay, so that is the function. It is doing nothing much. It is basically just printing a string. Okay, so now we come to main. And this is just for sanity checking that okay, you have not given any input apart from the running the program. So this is just some sanity check. You can ignore this part. This basically just says that okay, there should be only the file name and there should be nothing else, and then you just print the error and exit. So this part also is not very interesting, but let's come here. Now this is so the structure for the thread, it's called pthread underscore t, and now we declare two variables for these structures. So we want two threads, p1 and p2. Okay, and then this printf just prints that okay, now we have begun the execution in main. And then there is this function called pthread create. So if you make it, actually the thing is lowercase, which is there in Unix, but again, here this pthread creates just asserts. So I mean, if you just go here and if you see what is pthread create, it has the same thing. Thread, attribute, start routine, and argument. These are the four things which are there in a thread. And what this caps pthread create does is just calls pthread create with the same argument, exactly the same argument, and then just sees that everything goes fine. So it asserts that the return value of that is 0, and then that's it. So there's not much difference, but if you want to just use the Unix thing, it's small pthread create. So that it does not get you confused. Okay, so now and also I would want you to go through the next chapter, the thread API. It's called, and then you get more idea about what these arguments are for pthread create, and what does a thread have, what are the things that the structure of the thread has. So basically, it has four things again, the pointer to the structure, the thread structure, which you have declared. Then this one is okay. This is also an argument. Then this is the procedure that you want to be. This is a pointer to the function that you want to be executed in this thread. And then this is another argument. Okay, so I don't remember right now what is the second argument. So let's check. So the second argument was okay. Yeah. So there are some attributes which are whether you want it to have some priority in the program or something like that. So this is for that, and you can just pass it null if you don't want to do anything fancy. And so this is the pointer to the function, and this is the arguments for the thread. So here you can directly use whatever you want to pass on also instead of a pointer. So you have a string, and then pointer to that will get passed on. So this pthread create basically creates a thread of. So this initializes this structure pthread t, and then it starts running. Whenever you do this pthread create, it starts running. So this function will start running, and that's what you do for 2 times for the letter A and for the letter B. So 2 of them will run in parallel, and then the main program or what you want is wait for the threads to finish before you exit the main. It's not that you called and then you exit and so on, because then they'll run and you have not used their output or whatever. You don't know whether they have finished. So for that, there is this function called pthread underscore join. And again, this capital P is their implementation. And again, if you look at this thing, then it's again exactly the same. Pthread join is assert small pthread underscore join thread value pointer 0. So What does join do? Join makes the program wait for the thread. Okay. And this basically, this null pointer is for, if you want to use the argument from the return value of the thread, then it will be stored in this. But in this case, we don't want, we are not returning anything. So we don't care about the return value of the thread. So we just wait for P1 and we wait for P2, and then we end the main function and yeah, return 0. I mean, we print that we are ending the main function, we return 0, and then main also exits. So this is the program that we are going to run now. So any questions about this? About the program? Okay, so this is like a very simple program. I've already compiled it. So let's say this is T0, and so it prints main begin, then it prints A, then it prints B, then it ends. Okay, let's run it once more, once more, once more, once more. Okay, I'm not getting B, A today, but like last night it did happen that it printed B and then A. Yeah, but so what can happen is that the ordering can be different and you cannot predict that beforehand. But in this case, like, yeah, it's a small program, so maybe it's like doing not exactly deterministically, but maybe it's finishing A always. But yeah, yesterday it did happen that I got B before. So it's not always that you get the same output if you have not made some if you have not applied some mechanism to make the output deterministic in this case. Yeah. All right. So yeah, this is not happening to. This is not going to be a today at least. So cool. So this was the program, right? So why it can happen? Okay. So let me convince you using. Sorry. Let me convince you using some other logic that why this can happen, and that will also give you some idea into how these threads work. So okay. So we got this output, which was something like whatever. I mean, it had main, begin, then we just printed A, B, and then main, and something like this, right? So this A, B order could have been different. And let's see why. So suppose we have a single processor only. So let's not worry about parallel processing and so on for now. So the point is that the threads can run in any order. And this is decided by the scheduler. And generally, as we had seen earlier, also the schedulers can be very complex. So generally, you can't predict how the output is going to be. So let's see what can happen, for example. So let's say some possible traces. So first one is, so there are three threads basically in the program. So One is the main, one is, let's say, T1, and one is T2. T1 prints A and T2 prints B. Okay. So let's see how the execution would have happened. So here, let's say main T1, T2. Okay. So what happens? So first the main program starts. Okay. Then it prints the first thing, main begin. Okay. Then now it creates thread 1. Now thread 1 has been created, so it can start running, or maybe it creates both threads, T1 and T2, and it has still not released control, so now it's waiting, the join statement. So waits for T1. Now it has nothing to do, so it will release the control, and now maybe T1 comes into play, because so main is waiting, so T1 comes, so it runs, prints A, and then returns. Okay, so now the waiting for T1 is over. It has returned. So now it will wait for T2. Now T2 runs, prints B, returns. Now both of them have returned. So the main function prints main end and exits. Okay. So this is one possible, way of execution. What can be the other one? The other one again, so main T1, T2. So here, as I said, so it starts, then prints, whatever main begin, then it creates, okay, thread T1. Now T1 is created, so maybe T1 just starts running immediately. So it runs, it prints, and then returns. Okay. And then it creates thread T2. That was the second instruction. Now suppose T2 runs, prints B, then returns. Now main goes to wait for T1, but that returns immediately because T1 has finished. Okay. Then it waits for T2. Again, it returns immediately. And then it just prints the final message. Main end. And then it just exits. Okay. So this is the another way. So at least in these two, we have not seen the order being reversed. But there can be a third possibility also where, okay, so there can be main, there can be T1, T2. And here what can happen is, okay, main starts, prints, then creates T1, creates T2. Now it has created these two threads. Now these two threads are basically waiting for execution, and maybe T2 gets the chance to run first. So it runs, prints B, and then returns. Okay. Now suppose the control is transferred back to main. So it waits for T1, but T1 has not even started executing till now. So now the control goes to T1. So it runs, it prints A, and then returns. So now the wait for T1 is over. So since it has returned, so now it waits for P2, T2, and that returns immediately because T2 has finished. And then print main end. So these are the possible traces. So in this one, as you see that, B gets printed first and then A gets printed. Okay. So basically the point was to say that the threads can run in any order. Okay. So now, but here we did not do anything much. We just had two threads which just printed things. So the main idea, as I said, for threads to is to have some shared data. So the earlier no shared data. So suppose what we want to do. So we want to update a global variable using two threads for now. So we have a variable, let's say counter, and we want to increase it n times each by two threads. Okay. So let's see the program for it. Okay. So I hope you can see the screen again. Can you see?
Yes, sir.
So let's look at this program which does this. So okay, so again, ignore the headers for now, but they are not there's not much interesting going on there. I mean, it is a bit interesting if you see what they have done in these, just have a look, but it is not very hard to understand also what they have done, but that is not important for right now at least. Okay, so we have this integer max. It will tell the value of n, that how many times we are going to increase it. Now we have this volatile int counter is equal to 0. So what does why we use the keyword volatile here? So volatile is for, so suppose you have a variable and its value can increase at any point using different threads or something. So, and which basically it's not increasing by anything which is surrounding it. It's not obvious for the compiler, so you just declare it so that the compiler knows that okay, this variable can change any point at any point, because maybe different independent threads are going to have access to it. So so you declare these things globally, of course, because you want the threads to have access to them. Okay, not this one, sorry, this is a more complicated one. So let's open t1.c. Okay, so this is T1. So again, so we have an integer and we have a counter, the same thing. Okay, and now we have the procedure which will increase the counter. So we pass the, and here we pass as argument just the name of the thread, that okay, this is thread A or thread B, because we want to use the same procedure for both the threads. So just to differentiate between the threads, we send it the A and B so that we can, like, keep track of which thread is doing what. Okay, so and then we just put that argument in a letter, which, so basically for one thread it's going to be A, for the other thread this letter string is going to be B. It is going to be a string of size, like, size depends on what you call size, but it is A followed by null or B followed by null, so on. Okay, so now there is this integer I, which basically is going to be on the stack thread, right? So because it is declared here, thread stack. So the local memory for the thread, this integer is going to be there. It is going to be stored there. And then you just print the address of I just to see that, okay, this is going to be different, and its stack is going to be different. Okay, and then for I starting from 0 to the max, which is the counter, that how many times, not counter, I mean, which tells you how many times you have to increment, you increment the counter. Okay, so counter is equal to counter plus 1. So counter is this global variable. And then you just print that, okay, I'm done, and then you follow that by your name. Or with your name, you say that the thread is done, whether it's A or B, then you return null. So that is what the thread is doing. That is what the procedure is. And what do we have in main? So main, again, this is just that sanity check that, okay, you have given it an argument. It is not that you're just trying to run, just the binary. It needs another argument. So this just checks that, this part. And then you just convert the argument that is given to integer and store that in the max variable, which is declared globally. Then you again declare two threads, P1 and P2, using pthread underscore T. And then you do a printf that now we are going to begin, and the value of counter is 0, because, I mean, that's what you initialized it with, and nothing has like accessed this till now. Okay. And then you also put its address somewhere. You also might want to print its address. It's fine. So where is it, like, basically where this is going to be, just for that. Now you create a thread with like P1. So you have declared the variable P1 for the thread structure. Then you don't give any attributes. You give the procedure myThread, and you pass on the string A. Similarly, you pass on the string B, and then you wait for both of them to finish. Then you join, and then the main will say done. What is the value of the counter? It will print the value of the counter. So the first one is counter, and then the second one is max times 2, because each of the threads should increase the counter value by max amount. So finally, you should get twice the max amount to be the value of counter in the end. So is the program clear? Or is there any question about the program? Please ask, I mean, if there is anything not clear about the program. No? Okay. So now if I run this program, I think I have made, yeah, nothing to do. Okay. So let's say T0, T1, yeah, T1, and suppose I give it some argument, let's say 2. Okay, let's see. So the counter is 4 at the end, and it should be 4. But let's give it a bigger argument, 10. Okay, for 10 also it is the same. All right. 100. Very good. Oh, sorry. Okay, so now you see that the counter at the end is 18,980 while it should be 20,000. Okay, so let's, no, sorry, yeah. So suppose I give it some smaller also, sometimes then it works, sometimes it doesn't. Right now it is working, it seems. I mean, working as in it gives the same value, but if you give it higher, then it decreased even further. It is 15,000, now it's 17,000, and so on. Now it's 14,000, etc. So, yeah, so, and it's not that it is broken only for 10,000, even if you give it 20,000, okay, it worked. Now it didn't work. So, I mean, so what you can see is sometimes the output is going to be something, sometimes it's going to be something else, and we need to look into why this is happening. Okay. So yeah. So the now we wanted to do this, that we wanted to increase the variables using different threads, and we did that, but we found a problem that okay, the value is not exactly what it is. It should be. So basically, what happens is so why the unexpected output? And the answer for that is uncontrolled scheduling. Okay. So as we had seen earlier, that so the main statement that is like we want to execute is in both the threads is counter is equal to counter plus one, right? Now, if we write this into assembly code, then this is not an atomic instruction, and we had discussed that before also. That so it breaks down, let's say, into three. That first you move some uh, like whatever, like some value which is there in the uh, address space to some register. So let's say EX, and then you increment the EX. So add 1 to EX, and then finally move the contents of EX to the same address. So these three correspond to this one statement in C. Okay. So let's see what can happen. So suppose thread run one was running. So suppose the value of counter was 50 when we are going to start this analysis. So now suppose thread one is running. So now counter is 50. So counter value of counter was 50. That means this is in this location. Okay. So counter is 50 and it will be copied to EX in instruction 1. Okay. So EX is 50 after executing 1. Now 2 gets executed, or let's say after 2, EX is 51. because you increase it by 1. Now suppose a timer interrupt happens. And OS saves all the data, including registers, and it schedules, let's say, thread 2. Now thread 2 comes again, still at that memory location counter is 50 only. So it executes 1, 2, and let's say 3 also. So now counter is 51. And suppose then again interrupt occurs. And now this thread is descheduled, and suppose thread 1 comes back. So OS saves data. Thread 2, okay. Now suppose thread 1 comes back. So OS restores registers, etc. So now EX has 51 because that's what it was when thread 1 was rescheduled. So EX has 51. Now, and 2 instructions have been done. So its program counter is going to be on the 3rd instruction. So now 3 is executed and 51 is stored in memory. Okay. So counter is equal to 51. While what it should have been? What it should have been after both?
52.
It should be 52. So here we see that how this happened, that we wanted to increase it 2 times, but it increased only once. And this happens because of what is called a race condition. So when the outcome depends on, in what sequence something is happening, but that sequence cannot be like controlled by you. Some timing or sequence of events which cannot be controlled. Okay. So this gives us what is called an indeterminate result. Instead of deterministic. Okay. So we basically do not want like race conditions to happen, and so, and also there is one thing which is, which causes the race condition. So this is called critical section, which is basically section of code which, if being executed by multiple threads, can result in race condition. And so what we want is the property which should help is mutual exclusion. So this is like desired. And what does the term mean? That in this context is if one thread is executing a critical section, no other thread should. So this is what we want. And I mean, there is another thing that can be that, okay, maybe this is like being broken into many statements and that is why this is happening. So what if we don't have like, mm, such instructions like, which get broken up into multiple parts, and then we'll always be sure that either instruction has been executed or it has not been executed. But that that is not always possible because you're going to have complex instructions, and the hardware can only support so many things, and the programmer can write like many such statements and so on. So this is something that so basically the property that you would want is atomicity. But we still want some sections of the code to execute together, even though the hardware cannot support that. I mean, hardware cannot support that by itself, and that in the sense that it cannot make it a single instruction and so on. So we need to do some more things to do that. Okay. So maybe even as one instruction, but this part is not very practical from hardware point of view. Okay. And this will actually be achieved by what are called locks. And we'll see a quick example in this lecture itself, but we'll study them in more detail. So this is one thing that we would want. And another thing is what we might want is communication between threads. So maybe sometimes you would want a thread to sleep till some other thread has completed some task. Yeah. And it can be the other way around, or we might want that after completing some task, the thread makes up another one. So this is like communication between threads and all. So there is this thing called condition variable, which helps us with these kind of things, with the wake sleep sort of communication between threads, and we will also see that in one of the coming lectures. So before that, I would just go through one example of so this problem was happening in this program. So how do we solve this? So let's just see that using this lock things. So it's called a mutex, which is for mutual exclusion lock. And so this was the program. Okay, sorry, you cannot see that. Doesn't, I guess. Okay, so yeah, this was the program, right? So basically, what we can do, so what we want is for this line to execute together. Like we want this section to be atomic. So this is the critical section of the program, and we want it to be atomic. That this should not be broken into many like separate executions and so on. If it starts executing, so for that we use these things called locks. Okay, so a lock is the structure where like the name is pthread mutex t. Mutex is for mutual exclusion. Lock, and then you declare the lock using that. So these two programs are exactly the same, except like these lock lines that I'm just going to talk about right now. So you have the same counter, you have the lock, and then you need to initialize the lock here. Okay. So this is the initialization procedure. You need to do this to initialize the lock. So you give it the pointer to the lock, and then you just pass it null, and that initializes it, and then you assert that okay, this actually worked. So this is the initialization of the lock, and now the lock is ready to use. So the remaining program is exactly the same. That okay, you basically print the begin, then you create the thread with A, then you create the thread with argument B, and both are going to the same procedure, which is going to increase the pointer and counter, and the max stores again. It takes the input from the argument of the program, and then each of the threads increase it max number of times. So that is exactly the same program, but now we want to use this lock. So we declared the lock, we initialized it, so now it can be used. And so now how do we use the lock? We just use it here. We just call the locking procedure, and we use this lock. So locking procedure is called by pthread mutex lock, and this puts the lock. So this is the critical section protected by lock now, and now you remove the lock. So here you just use lock, and here you use unlock, and that's it. You use the same lock, and now so that means that this part, this statement will now be executed atomically, and it's not going to be broken down into I mean, it will be broken down into multiple statements for assembly, but all those statements will be executed together. Okay. So either all will be executed or none will be executed. This is not going to happen that okay, some of them are executed and some of them are not executed. So let's see how that works. So that is T2 actually. And if you give T2 any argument, so let's say again, let's give it 10,000. So this is always going to be like same. So even if you give it like 100,000 or a million, okay, it broke or what? No. So yeah. Okay, and then so this address of I we were printing, so you can see that they are in like uh, this is for A and this is for B. So these addresses are going to be in their stack. So this address is going to be in A stack. This address is going to be in B stack, and this the counter is. So the counter is going to be a global variable, right? So it will be on the heap. So its address is very small, as you can see, and these are like stack addresses that two of like different threads. So they're different. This is in the heap, So this was the address of counter. If you remember. Where? Here. Counter and the pointer to counter. So this is the address of counter. So this is what we were printing before also, but before I didn't discuss this, but that's like we can talk about it now. So main begins here and it prints the counter, the current value of the counter, that is 0, and then the address of the counter. And now A begins and it prints the address of I, then B begins. And here you can see that B is done first and then A is done. Right? So this is what I was talking about, that okay, it didn't happen before, but it happened. No. Yeah. So here A is getting done first, then B is getting done, here B is getting done first, then A is getting done, and so on. So yeah, it is still you don't know in which order the threads are going to like finish or start, but now at least you know that okay, they do what they are supposed to do, that they increase the counter by 1 every time, and it gets reflected in the counter. It's not that the in between thing will be lost, and that is done by using these logs. So again, for the logs, you can. I would request you to go read it from the next chapter, which is the thread API, and it talks about this threads. So it also talks about this join. How does join work? How does the pthread create work? So, I mean, the basic things are very easy. You declare a thread, and then you just pass the pointer to that thread that you have created with some attributes and the procedure and some arguments. But if you want to see it like in little more detail, I would ask you to go read the next chapter, which is about process APIs. So they talk about pthread create, and that is the the most. I mean, it has like 4 arguments and so on, but it's not that hard to understand. And then pthread join is just like you wait for the thread, and this is used for the return value of the thread. And then it also talks about the locks, the basic functioning of the locks and how to use them. And as I said, that is again quite simple. You just declare the lock. You declare it like globally so that it can be used by both the procedures, and then you initialize it. So that is an important part which you shouldn't miss, because I mean, in some systems, so Linux I think initializes it, but Mac I'm not sure whether it does or not. So you should anyway, like, it's a good practice to initialize the structure that you've declared. So you initialize it, and that is if the initial thing is not in the format that the lock needs, then it's not going to work. And then you just put this lock before the critical section of your code, and you just put their lock, pthread mutex lock, and then when you're done, you just put like unlock. So you remove the lock, and then you do this. So any questions about this code? No questions? Okay. So yeah, so that's all I wanted to do for today, and yeah, I would. So these programs are available anyway online. If you go on the book website, and then you can like do it by yourself and play with it, and see how these things work, and what if you make some changes somewhere, and how does that affect things, and so on. So yeah, that will be really helpful for you to understand these things in more detail. And yeah, right now it's not at like assignment level that I can actually give an assignment that can be evaluated, because these things have been just introduced. But I think this is also good enough for you to just start programming a little bit using threads. So that can be like an ungraded homework or something. So yeah. Okay. So also about the exam and also there were some regret requests. There are some queries. So I was busy over the weekend. I'll go through them and try to resolve them by tonight or tomorrow or something. So today 5 p.m. is the time by which you can submit the regret requests. And assignment one, I hope everybody has got their grades and it's done now. Assignment two will be evaluated shortly, and you'll be will be sharing the like marks for the second assignment also. Like yeah, at some point. So, any questions about that or anything? No. Okay, cool then. Thank you everyone, and I'll see you on Thursday.